Hi everyone, welcome to our second lecture on arrays. We are going to have two lectures today. We are going to talk about arrays first. We are going to talk about the additional issues in arrays that we actually haven't talked about last time. Like for each loops, we are going to talk about algorithms with arrays, like for instance, linear search, binary search, sorting algorithms like select sort and insert sort and bubble sort and quick sort and so on. So let's continue from where we left it last time. We learned how to create arrays, we learned how to iterate over the elements of an array using index variables, but since Java 1.5, Java introduced a new type of loops that enables us to traverse a complete array sequentially without using an index variable. And this kind of loop is not only used for arrays, but for any kind of collection that is implemented in the Java collections framework. It will allow users to actually iterate over elements stored in trees, in graphs, and so on. So for example, we created earlier last class a list of the type double, my list. It was an array of 10 elements of the type double. If we want to iterate over the elements of the array, we can write that with a for each loop for every variable of the type double value. In that collection of elements, in our case the array my list, we can actually iterate over the elements of the array by using the variable value. In general, the syntax is for every variable value of the type of the element type in the array reference variable, we can use that value for computing any kind of expressions. Now, the way that it internally uses, it actually iterates over the elements of the array. It copies every element value and it copies it into the variable value. So we can use for each loops, for instance, with primitive type variables, primitive type arrays, we can use the value to actually compute expressions. However, we cannot use this new variable to assign new values to the primitive type arrays. And the reason for that is that we actually have a copy of the element in the array. So we cannot assign a new value to that variable and actually modify the elements in the original array. So let me actually show you an example. And the example is actually the one that we see here. We are printing the value of the elements of the array. So let's go to Eclipse. I have the previous program that was just a test. Let's create a double array. Let's call it my list. Is a new double array of 10 elements. By default, they were all initialized with 0, and we are going to iterate with a for each loop for every double v in the array my list. The name of the variable is really not important. You can actually call this variable anything that you wish. We will print the elements of the array with the system.out print the variable v. If we also want a space after each double, we can actually add the space in that print statement. So if we print it, it actually prints that there are 10 elements in that array. All of them are of the value 0. As I told you earlier, if you will try to actually modify the array, so if we write another for each loop in the same array of integers, and you would want to assign to every v a different value, like 1, and you print again the elements of the array, it will still print 0.0 for every element of the array. So after the first half, the second half is basically still 0.0. And as I said earlier, the reason for that is that we actually iterate over the elements of the array and we copy the value of those elements into the variable v. So modifying the variable v will only modify that local variable v. It will not modify the elements of the array. However, these loops are quite useful for iterating over the elements and basically computing any kind of values from those elements of the array. So for instance, one thing that we could do is to actually sum the elements in the array to compute the total of all the elements in the array. So for that we will define a new variable total equal with 0, and then for every value in that array we increment the total with the value of the element in the array. So in this case it will actually compute in the total 0 because the value, the elements in the array have the value 0. All have the value 0. So if we don't print the elements of the array, we basically just compute the total and we print that total, it actually prints 0.0. That's the total of the elements in the array. To make sure that this is actually correct, let's also initialize the elements in the array with random values. And as I said, in order to do that, you really need to actually iterate over the indices of the elements of the array, as long as I is less than the length of the array. The value of my list of the index I is, and now we can actually compute some random value like math.random multiplied with 100. So in this case, printing the total will print actually the sum of the elements in that array. And if we want to iterate over the elements of the array and also print those elements, we can do it with a for each loop. For every double v in my list, let's add a space and a new line after we actually printed the elements of the array. Sometimes Eclipse does more than actually it should, but that's okay. Okay, so let's return to our lecture. So this kind of enhanced for loops are basically shorter versions of the for loops. Since Java 1.5 or Java 5, the for each loops are more general and you can use them with any Java collection. You can use them to basically sum the elements of a matrix, for printing the elements of an array or matrix, and so on. Now, we learned how to sum the elements of the array. What about how are arrays actually internally stored? Arrays are actually reference type variables. So when we assign to an array the reference of an array of doubles, if we actually assign to any other array basically the same reference, we actually have two pointers pointing to the same content. So let's assume that in a program we have two lists. One is pointing to a list of elements and another one is pointing to another list of elements, and then we have an assignment that list 2 is assigned list 1. What happens is the fact that the pointer, the reference that is that exists in the list L2 is modified to the address of the first list. Therefore, the old list is in fact empty. We didn't copy the elements from the old array into the new array. We actually redirected the new array reference to the same list as the first list, list 1. So why is this important? It's important because of the fact that, in fact, now if we modify the indices, the elements of any one of the two lists, the other one actually sees the same results. So let's actually do a simple example and see that this is in fact the case. So we can actually create two lists. Let's call them list 1 and list 2. And we can actually create them in line. So for instance, list 1 is the set of elements 1, 2, 3. And we create the second list, list 2, which is another list of elements, like for instance 4, 5, 6. However, at this point, list 2 is assigned the value of list 1. If we print the elements in list 2, it will print the elements from 1 to 3. However, let's say that at this point, list 1 of the element at index 0 is assigned 7. So we actually modified list 1 element at index 0. However, that is also visible in list 2. So now the first element of list 1 is in fact 7.0. And the same happens if we actually modify list 2 of the element at index 0 is assigned 8. If we print the value, let's actually just print that value of list 1 of index 0, it will be reflected the fact that actually the two references are actually pointing to the same element. So list 1 and list 2 of element at index 0 is in fact now 8.0. So we actually have two variables that are aliases to the same location in memory. So in fact, modifying either one of them, using either one of them to modify the content will be reflected in both of them. And this is exactly what happens when we call a method with a list, because we actually invoke that method with a reference to an array that is in the heap. Now, if we want to copy arrays, as I said earlier, we need to create a new array, and this is different than actually just redirecting the elements, the two references, to the same position. So equal cannot actually be used for copying arrays. You are actually redirecting the pointer. In order to copy arrays, the only way to do it is actually to create a new array of the same size with the original array, and to copy one by one all the elements from index 0 to the length of the array from the source array into the new target array. So let's actually see this, and the fact that these two arrays are now disconnected. It's not the case that we are actually connecting the two arrays into one and using two variables to access that new array, but that we are actually copying from one list to another, and the changes made in the first list are not reflected anymore in the second list. So the code that we just saw in the lecture notes is that list 2 is a new double array of the same size with list 1. Then we iterate over the elements of list 1 with a classical for loop for every integer I starting from index 0, as long as I is less than the length of list 1. And the action after each iteration is that we increment I with 1. The element at index I in list 2 is assigned the value of the element at index I in list 1. So now if we actually print the elements of the list, in list 2, these elements are in fact the same elements 1, 2, 3 that we had in the original list. Now, if we modify any one of the elements in list 1 to a different value, let's say again 7, that will not be reflected anymore in the second list. So for instance, if we print the elements in list 2, those are 1, 2, 3. If we print the elements in list 1, those are the new elements 7, 2, 3. So the two lists are actually what we would probably wanted, to actually have two lists which we copy the elements from one list to the other. There is already a utility that does exactly the same thing in the system class that is imported by default from Java Lang, the core package that is imported in Java. And this method takes the source array reference, the position from which it starts copying, the target array reference, the position in which it starts copying the elements from the source, and the number of elements that it needs to copy. So the same code that we wrote previously, instead of actually copying the elements explicitly, we can use system.arrayCopy. And again, we have to give the source, in our case list 1, the position from which we start copying, the destination, in our case list 2, the position from which we start copying, and the number of elements that we need to copy. So this actually has the same effect as the previous code. Instead of iterating over the elements explicitly and copying the elements at every index in the corresponding index in list 2, we actually copy the entire list with this method. The implementation is quite simple. It's actually exactly the same that we had before. We iterate with a for loop over the elements from the given index and the number of elements. And we actually assign them to the corresponding elements in list 2. So let's actually talk about the issue of passing arrays to methods. So passing arrays to methods, in fact, passes arrays in the same way that you do assignment of elements from one, assignment of lists from one list to another. But I see that there are questions on the chat, so let's actually respond to those questions. So Mutasir is asking if list 2 is equal with list 1, we can change the value of list 1 everywhere and it will change it everywhere, meaning in list 2. Yes, of course. I think what it means is that list 1 and list 2 are referring to the same object in the case that we have list 2 is equal with list 1. However, if we copy the elements from list 1 one by one into list 2, now we have two independent lists. So changing the elements in list 1, it will actually not change the elements in list 2. Excellent. Thank you. Very good question. So passing the arrays to methods will actually copy the reference of that array into the method formal parameter, which means now that both references, the original array reference and the reference that is a formal parameter to the method, are actually pointing to the same array in the heap segment of memory. So we can actually use the reference to actually iterate over the elements using basically the length, and or we can use a for each loop to iterate over the elements. The only new part that we actually have is the fact that you can create arrays on the spot. So you don't need to create a new reference in the main method that is equal with some array, and to basically create the reference and maintain it in the main method, you can create references directly when you actually pass it to methods. The difference between using the interned arrays or arrays that are created on the spot, we actually pass also the type of the element, the list, when we actually create the array inside method invocations. So for instance, when we have a print statement and we create a new integer array, that will create an array of that given type with the elements in the array. The same syntax can also be used for creating or initializing arrays. However, in this case, we have no explicit reference variable for that array that was created when we invoke the method. Such arrays are called anonymous arrays because of this fact that we don't have reference type variables. So Java uses pass by value to pass arguments to methods. For a parameter of a primitive type, the actual value is passed, and therefore we actually have a copy of the actual parameter into the formal parameter. If the formal parameter is changed inside that method, it doesn't change the actual parameter in the main method. However, for an array type variable, the value of the parameter is actually a reference to the same array. So if we pass this reference to the method, any changes of the array elements that occur inside the body of that method will actually also affect the original array elements because they are the same references to the same elements. In order to understand that, let's actually do an experiment. And in this experiment, we create two variables. One that stores a primitive type variable, 1, and one that actually stores the reference to an array of integers that is represented on the heap. We pass both variables to a method m that takes an integer and an integer array, and we modify within the method m both the number, which is basically a primitive type variable, and numbers of 0, which is the array of integers. When we return from that method and we print the value of x, x is still 1. If we print the value of y of 0 will be 5555. And the reason for that is really that when we actually pass those two values to the new method, we are copying the values. It's called by value. So basically, all the objects like arrays or other type of objects, user-defined objects, are kept in a separate area of memory called the heap segment. And this contains all the dynamically created objects using the new operator. In the case of arrays, we always use this new operator, new integer array or new double array of the number of elements. And all of these are actually allocated in the location of memory, and the variable itself is a reference or the pointer or the address of that location in memory. So when we actually invoke a method, like in our case the method m, we are copying the reference and the primitive type value into the formal parameters, number and numbers. So if we change number to a different value, that is not reflected in the variable x. However, if we change numbers of 0 to a different value and we return from that method, that is reflected in y of 0 because y is a reference to the same array. So there is the difference between primitive types, the fact that values that are of those 8 primitive types that we talked about in the first lecture this semester, which are basically the whole numbers, byte, short, int, and long, and the real numbers, float and double, and the Boolean type and the character type. Those are the values that are stored directly where the variable is an alias to. The variable is an alias to a location in memory, on the stack. In the case of arrays or any other types, basically reference types that are objects in Java, like string and so on, the variable itself is an address or a pointer to a location in memory. So when we actually change the data fields, or in this case the elements of the array, it will actually be reflected by all of the other references that are pointing to the same location in memory. So let's actually do this experiment because it's very important that we understand the difference between primitive types and arrays in Java. So again, we are going to return to our program. So first we create an integer variable x and we assign it the value 1, and we invoke the method m of x, and we print out the value of x after we return from that method. The method takes as an input x, so it's a public static method that doesn't return anything. Internally, it will assign to the integer x a new value. So let's say that we assign 1001. When we modify the local variable x, but that does not modify the variable x, the actual parameter in the original method. Because what happens is that it passes the value of that global x or x in the main method. So let's actually say that this is the local x was originally, and after it was changed is the new x. However, the global x, or let's say the main method x, is still the value 1. And we actually can see that that is the case both before we invoke the method m and after we invoke the method m. So let's use println so we can actually see easier what happened. So before we invoke the method m, x is 1, the local x is 1, the local x will be 1001 after we modify it, and after we return from the method m, the main method x is still 1. Okay. Now let's modify this program and actually create an array that takes an integer 1. And we leave exactly the same. Let's actually print the fact that we are printing the element at index 0. We invoke the method m with this array of integers. We again print the value at index 0. We assign to that x the value that is an array. And we print again the value of x. And in fact, we can even see the fact that x is in fact a reference. So let's actually print x without So now if we run it, it basically tells us that x is an integer array at this location in memory. So it's actually a reference. The main method x of 0 is 1. The local x was 1. Then we modified it to 1001. In all of these cases, the actual output should be the fact that we are actually showing the element at index 0, really. And when we return from the method, we actually have the same reference, but the global x is 1001. So when we actually call a method, we actually call it with a reference. And that reference is passed to the inner method. In fact, we can actually also print the value of that x, the local x, is still the same reference, is still the same address in memory. So x, the global x, is a reference. After we call the method, the local x is still the same reference. So modifying x of 0 will modify the global x as well. Any questions? Yes, that's completely true. Basically, the second example that you have would create an array that has the elements 0. So basically, the equivalent for what I just wrote above would be the fact that we initialize x with a new double array of one element, and then we assign to x of 0 the value. Let's work with doubles here, or with integers. the value 1. So basically what we wrote above, the fact that we assign directly to x an integer array that contains the element 1, is equivalent, is really equivalent with creating an array of the size of that default initializer for arrays, and then assigning to each element the correct value, the value that we need. Okay, great. Okay, so what about when we return an array from a method? For instance, we want to write a method reverse that, given an array of elements, let's say integers, it creates an array of the same size, but the elements occur in reverse order. We are actually returning a reference to an array that was created on the heap, but the array was created from the method itself. And that reference is an array of new elements that are actually in reverse order of the original elements. And in this case, we are actually using a for loop that iterates with two variables, loop variables. One of the variables I is initially initialized with 0, and the second variable is initialized with result.length, -1. So basically, we have two variables. The first variable iterates over the elements in the original list. The second variable iterates over the elements in the resulting list. So we start with the first element in the first list, and we start with the last element in the second list. As long as I is less than the length of the list, so we increment I with 1 after each iteration, we assign to list of to result of j the element at index I in the original list. After each iteration, we increment I and we decrement j. So in the original list, if we had some elements like 1, 2, 3, and so on, they will occur in exactly reverse order in the resulting list. So for instance, if originally we have from 1 to 6, the reverse of that list will actually be a pointer or a reference to a new list that contains the elements from 6 to 1. And let's actually implement this. It's very important that we always try all the code that you will see in the lecture notes, because it's very useful for actually learning these topics. So initially we have an integer array, let's call it L1, of elements of the type integer. This is equivalent to actually defining that this is a new integer array with those elements. And then we actually create a reference L2, which takes as result the method reverse output of L1. And if we iterate with a for each loop, now we know how to write those, over the list L2, it should print the elements in reverse order of the original list. So let's implement the method reverse. Returns the reference of an array of integers, takes as an input an array of integers or the reference of an array of integers. Let's call it L for list. The variables in the method do not have to actually have the same name with the variables in the main method. We can create an integer array reverse, which has the same size with the original array. In the end, we are going to return that reverse index or reverse reference, and inside the method we are actually going to write this for loop for every integer I that starts from 0 and j that starts from the length of the original list -1, as long as I is less than the length of the list. We increment I with 1 after each iteration, and we decrement j with 1 after each iteration. Result of j is assigned L of I. So that basically implements, let's call it reverse, we called it reverse. That implements the reverse method. Basically, when we print the elements in the second list, they are in reverse of the elements in the first list. So now one question that some of you may have is, what if we only pass the array and we modify the elements of that array in place, in the method reverse? So we are not returning anything from the method reverse itself, and the method reverse itself actually modifies the elements in place. So how do we actually implement that? We are not going to create a new reverse array. We are not going to actually assign the elements. We are going to swap the elements in the same list. So in that case, we actually have to iterate over the elements in the array up to half of the elements of the array. And for every element, we actually need to swap the element with the element from the end, the corresponding element from the end. For that, we will need a temporary variable temp. So what we are going to do, we are going to assign to temp the element at index I. We are going to use the element at index I to assign it the value of the corresponding element in mirror, considering the middle of the list. So that will be the element at index L dot length of the list minus I minus 1. So for 0, we would like to assign the element at index length of the list minus 1. So that would be length of the list minus the value of I 0 minus 1. And then to that element, we would assign the value of the temporary variable, which store the element at index I. We don't need to return anything because we are actually modifying the elements in that reference. So when we return from the method reverse, in fact, we have in the original array the elements in reverse order. So if we print them, it will be 6, 5, 4, 3, 2, 1. Now the question is, why do you think I went up to half of the list? Because if I would continue, I'm reversing back the elements. So basically, to the element at index 0, I would assign the element at the last element of the list. And so I will, after I swapped all the elements up to the middle, I continue and I swap them back to the original position. So that's why I'm going only to half of the length of the list. This algorithm is in fact in the lecture notes as the next method after we actually trace the original method reverse. So tracing the original method reverse, it basically creates a new array result of the same number of elements as in the original list. Initially, all of these elements have the index 0. Then I create two indices, I and j. I is 0, and j will be 5, which is the length of the list minus 1. And then, as long as I is less than the length of the list, result of j, which is result of 5, the last element, is assigned list of I. And list of I is list of 0, which is 1. So basically, I copy the element from the first position into the last position. Then I increment I to 1, and I decrement j to 4. And result of 4, which is the previous to last element, is assigned the second element in the first list. And the process continues to basically assign the elements in reverse order. The moment that we basically get to the end, the result reference is returned as list 2, and now list 2 is pointing to the reverse list, to the elements in the reverse list. And if you don't want to return the elements from the array, you basically can actually modify the elements in place. So you don't really need to return the array from the method. You can actually just modify the elements in the current array. And you can go up to the half of the list. You can also use two indices instead of actually doing that length of the list minus 1 minus I to actually swap the two elements that are at corresponding positions. So what about searching arrays? Searching arrays is a method that basically takes a list and a key. And the key may or may not be in the original list. So how do we actually do it? The simplest mechanism, which is called linear search, requires comparing the key with every element from the list of I for every index in the list. If we find that key, we would like to return the index where we found that key. So the type that is the return value type for this method is integer, is actually not the type of the elements in the list, is the type of the index that iterates over the list. So as a simple example, let's assume that we are looking for the element with value 3 in the list that contains the elements 6, 4, 1, 9, 7, 3, and so on. So we compare the key with the first element, if they are not equal, with the second one, with the third one, and the fourth one, and so on, up to when we actually find the element in the array and we return the index of that element. So it's called linear search because it linearly searches for the elements in the array. So if we would have to implement it, it basically is just a for loop that iterates from position 0 up to the length of the list, and it compares the key with every element, and it returns the position of the first occurrence of that key in the list. If we finish the for loop, we finish looking at all the elements we found, finding the element, we return a negative index, because negative means that we haven't found the element. A normal index would be between 0 and the length of the list. So we return a negative index because we didn't find the element. So for instance, if we are looking for 3 in this list, we return 5, which is the index of the element 3. We start counting from 0 because in Java and in fact most programming languages, the index of the first element of a list is 0. So 0 is the index of 6, 1 for 4, 2 for 1, and so on up to 5 is the index of the element 3. Therefore, the element 3 was found at the index 5. If we look for minus 4 is not in this list, so we return a negative index. If we look for 4, it would return the index 1. What about if we are actually, the array is already sorted? For that, we want actually to find a better method. So let's assume that we are looking for a name in a phone book. We are not going to do linear search. Linear search will actually involve reading the entire phone book in case that the name is not in the phone book, or reading up to the name in the phone book, which is totally non-practical. So what we have to do is actually to iterate over the elements, but in a different way. Instead of iterating over the elements, since they are sorted, we can actually open the phone book in the middle. And if the name that we are looking for is before that, let's say the first name in the middle of the phone book, then we can already discard half of the book, because all the elements greater than the middle element will be also strictly greater than the name that we are looking for. So it should be cheaper to find the element, and we can actually apply the same algorithm for the rest of the phone book. We always compare the element that we are looking for with the middle element of the array. And then there are three possibilities. If the key is less than the middle element, we actually only have to search for the key in the first half. If the key is equal with the middle element, we actually found the element and we return the index. If the key is greater than the middle element, then we need to search only in the second half. We basically discard the first half. So how do we do it for, let's look for 8 in this array? We actually compare 8 with 4. It's bigger, so we can discard the first half. We need now the range from the middle index plus 1 up to the end of the array. Then we compare it with 7. 7 is still is less than 4, so we can discard both 6 and 7, and then we find 8, which actually we found 8 in 3 steps, which in linear search will take us much more. It will take us 8 steps or 8 comparisons. So how do we get to such a solution? We actually need 2 indices. The index of the element, basically the lowest index that we are looking at. In our case, we start from 0, the first element, the index of the first element. and the highest index of the range of elements that we are looking for. So we start at the beginning with the last element, the index of the last element, the length of the list minus 1. And then looking in this window, we basically compute the middle index, which is low plus high divided by 2. That's the average of the two indices. That's the middle of the range that we are looking for. If the key is less than that middle element, the element at index middle index, then high basically becomes middle minus 1. That means that we don't have to look up to the last element, we can look up to the middle index minus 1. We discard the second half of the array. If we found the index, the key, if the key is equal with the element in the middle, then we return that middle index. Else, we assign to low middle plus 1. And we execute this until we either find the element and return from that method, or the high is not anymore greater than low. That basically means that the high now becomes lower than the low, and we found the position where the element should have been, but it's not. In that case, we actually return a negative value that represents that position, minus 1, minus low. It actually tells us where the element should have been as a negative value, but it was not in that sorted list. So for instance, let's do this example. If we have an array that contains the elements 2, 4, 7, 10, 11, 45, 50, 59 up to 79, and we are looking for the value 11. This is a sorted array, so first thing, low is the index 0, high is the index 12. We compare 11 with 50, and 11 is less than 50. So now high will become middle minus 1. So we discard the higher half of the array. At this point, middle is again the average between the index 0 and 5, which in our case is integer average is 2. The quotient of the division of 5, the sum of low plus high divided by 2. And we compare 11 with 7, the element at index 2. 11 is greater than 7, so now we move low to middle plus 1, which basically looks at only at this array. And since the key is equal with 11, basically the list of 4, we return 4 as the index of 11. Now it really happened that actually the element was at that index, but if the element is later, like for instance, after the second half, we always get a better score to find the element with binary search. And is in fact much better score. It's logarithm in base 2 of the length of the list. And why is logarithmic score? Because, or complexity or efficiency, because at every step we discard half of the remaining array. So at first step we discard half, then at the next step we discard half. And this continues up to when we find the element. So instead of paying the size of the list for finding the element, we actually pay the logarithm of the size of the list. So for, let's say, 1,000 elements, instead of paying a score which is equal with 1,000 in the worst case complexity, we would pay logarithm in base 2 of 1,000, which is much lower. And we have a few more examples in the lecture notes. You can actually try to invoke all of these examples to see how many steps are in fact executed at in each one of these arrays. So again, let's actually implement the algorithm. The algorithm is quite simple. Let's assume that we have a sorted array. It doesn't have to contain the elements in order, not in order, but basically consecutive elements. Let's actually take the elements that are here, 2, 4, 7, 10, 11. 45, 50, 59. 60, 66, 69. 70, 79. and we want the index of let's say binary search, in this array L1 of the element 70. And in order to actually see that that is the case, let's print that index element at that index. So the method takes an array L and a key. In our case, that will be 70. First, we start by assigning to two variables of the type integer the indices of the range that we are looking for the element, and that is from the first element to the last element. And the last element has index, the length of the list minus 1. Then, as long as high is greater than equal with low, we actually do that comparison. First, we compute a new index, middle, which is the value of high plus low divided by 2. That's the index of the middle element. We compare the key with that middle element. If the key is less than the middle, then we assign to high middle minus 1. Else, if the key is equal with the middle element, then we return that index. Otherwise, we assign to low middle plus 1. And as I said, if we don't find the element, we return minus 1 minus low. And that is an approximate position where the element should have been if we would have found it. I think we don't match the current number of parentheses for this program. So let's see where yeah, I had an extra curly brace. So it returns 70, which is exactly the element that we were looking for. And if we only print the index, it actually prints the index of 70, which in this case is 11. Okay. Let's see if there are any questions in the chat. So why is it L.length? L is the variable that we are actually using inside the method binary search. So I believe that probably, let's call it list is better than L, because L could be confused. Let's rename L into list everywhere. Okay, could be confused with 1, and the meaning is not really 1, it's list of the length of the list minus 1. Okay, great. Binary search, there is a method that already is in the Java API. It basically sorts the elements of the, it takes the elements of the list sorted and it finds the index. Java.util.arrays.binary search is that method. I personally always prefer to implement my own. The complexity is the same, so It actually is just experience and practice of programming. Next problem that we try to solve is sorting. So sorting is a problem that we actually pass an array that is not sorted, and we want the response, the output, to contain the array that is sorted. So the simplest method for sorting is called selection sort. Selection sort, for every position in the array, it finds the minimum element from that position to the end of the array. Then it swaps that position, the element at that position, with the minimum element. Now we know that that first element is in the correct position. Because it's the minimum, all of the other elements will definitely be after it. For the rest of the array, we actually again search for the minimum or element in the rest of the array. In this example, 2 is the minimum element. We swap it with the element at index 1, which is the second element of the array. And we know that now the first two elements are sorted, because all the other elements should occur after them in the sorted array. And we continue this process always for the rest of the array to find the minimum, swap it with the element at the current position, and continue with the rest of the elements. If the minimum is already in the position that we are actually that we wanted, then it's already sorted. So we continue with the rest of the array up to the last element of the list, which basically gives us the sorted elements of the array. So if we need to implement this program, it's actually quite simple. For every position starting from index 0 up to the end of the array, we have to find the element, the smallest element in the list from that position I to the length of the list minus 1. And we need to swap the element at the index list of I with the minimum if it's necessary. That basically means that if the position is the same with the position of the minimum, we shouldn't swap them. So now we need to implement these two parts, which we actually did in some of the previous lectures. In the previous lecture, in array 1, we actually found the largest element of a list. The same way we can do the minimum element of a list. We assign to two variables, double variable current minimum, the element at index I. The current minimum index is the index I. In a for loop that iterates from position I plus 1 to the end of the list, if the current minimum is bigger than the element at index j, then the current minimum is not minimum, so we need to assign it the element at index j, and then the current minimum index is j. So this will compute the position in the current minimum index and the element that is the minimum index element in the array. And then if we basically, the current minimum index is different than I, we need to swap the two elements. So the current minimum index should be assigned the element at index I, and list of I should be assigned the current minimum. We can put everything in a single method. So this method iterates over the entire array. For every position I, we find the minimum in that array, and we swap it with the element at index I. Okay? So this method is quite simple. It basically finds the minimum of an array. A similar method is insertion sort. So insertion sort considers that the beginning of the array is sorted. So for every element that occurs after the sorted prefix of the array, we need to insert it in the correct order in the prefix that is sorted. So for instance, we consider that 2 is already sorted. If we would have to insert 9 in the prefix that is sorted, it will be after 2. If we need to insert 5 in the sorted array to 9, it will be before 9 and after 2. Now we can consider that basically we have the sorted array 2, 5, and 9. We need to insert 4 in sorted order in 2, 5, 9. So basically it will be before 5 and after 2. So what happens is that we need to shift right all the elements starting with from 5 to 9, and shifting right will require to actually iterate from the end to the beginning and shift every element one position to the right. And then we should assign the value that we saved from the position, from the new position, into the position that it should have been in sorted order. So we have repeated this until we reach the end of the array, and now we have a sorted array of elements. So again, we can actually implement it by breaking this problem into smaller problems. The first problem is actually to find the position where we want to insert the element in sorted order. So we can actually do that as follows. First, we start with the position equal with 0. As long as the position is less than the index I, which basically is the highest index to where we consider that the array is sorted. If the element at index position is greater than the list of I, then we break. That basically means that we actually found the position where it should be inserted. Then we need to shift right the elements from that position, basically from position, to I. But we have to do it in reverse order, because we basically shift the elements of the array right with one position. We have to start from the end so we don't override the elements to the right. So starting from j equal I, as long as j is greater than that position where we stop, list of j is assigned the element at index list of j minus 1. When we finish that loop, now we can insert at that position the temporary element, which is list of I. This will actually have this prefix sorted up to that position. And in the lecture notes you have a complete method to do that, including a test method main that actually tests this method on a random array of integers or doubles. Arrays.sort implements this. Since sorting is quite frequent in programming languages, you don't always have to implement your own sorting method. Okay. So let's do an example of sorting, and then we basically do the lab for the day, followed by the multidimensional arrays. I like to actually do more experiments with arrays before we actually do multidimensional arrays. So what I recommend at the beginning is to actually try to do your own sorting method. So let's actually sort elements in place with selection sort. Let's take an array of elements, random numbers or pseudo-random, and we want to sort those numbers. So we sort L1 in place, and we iterate over the list to print the elements after it was sorted. So for every integer v in L1, we use a for each loop, we print the value of v. Okay. So let's implement the method selection sort. So the method doesn't actually return anything. It sorts the elements in place. Let's call the list of elements A, so we don't confuse it with 1. And again, how it iterates for every index in the array. Let's start from 0. As long as the index is less than the length of the array. First, we need to find the minimum between I and the length of the list. Okay. So for that we define an element current minimum, which is equal initially with the element at index I, and current minimum index which is the index I. Then in a for loop that iterates with a different variable j, starting from the value of I plus 1 up to the end of the array, as long as j is strictly less than a.length, and j is incremented with 1 at every step. If the current minimum is not the minimum, is greater than the element at index j, we should really assign to the current minimum the element at index j, and to the current minimum index, the index j. After we do this, after we iterate over all the elements and we found the element with the that is the minimum, we need to see if we need to swap the elements. If I is different than the current minimum index, then we assign to A of current minimum index A of I, and to A of I the current minimum. So now if we run this program, it basically sorts the elements in order. Okay? Good. So at this point, let's save the lecture for your colleagues, and I will respond to any questions that you may have in the chat. Okay? And we will take basically a break so you can work on the labs. I would ask the TAs to actually solve the labs for you in SB Connect, and if you have any questions, we will take them in SB Connect. I will make the TAs hosts in a couple of seconds, and they will go over the lab together, and they can actually also record the lab, so your colleagues can actually see it later when they watch the video.